Hello everyone. In today's lesson we are looking at similar solids. Our objective is to find and use the scale factor of similar solids. What are similar solids? Two solids with equal ratios of corresponding linear measures such as heights or radii are called similar solids. So basically we can say two solids are similar if the ratios of their heights or their radius are the same. Identifying similar solids. Decide whether the two solids are similar. If so, compare the volumes of the solids. Example A. The solids are not similar because the ratios of the corresponding linear measures are not equal, as shown. So if we take a look at their lengths, this length over here is 5, this one is 3, so we can write a ratio of 5/3. Let's take a look at the ratio of their widths. The width over here is 5, the width over here is 3, so we can write the ratio of the width as 5/3. So far it looks like our solids are similar because the length and the width have the same ratio. Let's also take a look at the height. Our height in this triangle is 8 and in this triangle is 6. So we can write the ratio as 8/6, which we can simplify by dividing both 8 and 6 by 2. If you divide 8 by 2, you get 4, and 6 by 2, you get 3. Notice that this ratio of the height is not the same as the ratio of the lengths and the widths, and so the solids are not similar. In part B, the solids are similar because the ratios of the corresponding linear measures are equal, as shown. The solids have a scale factor of 2:1. I'm going to show you how they got this scale factor. So let's take a look at the length of the big prism and the length of the little prism. That's 10/5. Both 10 and 5 are divisible by 5. If you take 10 divided by 5, you get 2. 5 divided by 5 is 1, and so we have a ratio of 2/1. Let's take a look at their widths. The big prism has a width of 6 and the little prism has a width of 3. So we can write the ratio as 6/3, which 6 and 3 are both divisible by 3. 6 divided by 3 is 2. 3 divided by 3 is 1. Again, we have a ratio of 2/1, which is the same as the length ratio, which is 2/1. Finally, let's take a look at the heights of the prism. The big prism has a height of 14. The little prism has a height of 7. So I can write the ratio as 14/7, which 14 and 7 are both divisible by 7. So 14 divided by 7 is 2. 7 divided by 7 is 1. All of the ratios of the side measures of the prisms are equal. They're both 2:1. So we can say the big prism is similar to the little prism. Now that we know that the two prisms are similar, we can go ahead and find their volume. Remember, the formula for volume of a prism is base area times height, where your base area is the area of the base, which in this case is 10 times 6, which is 60, times your height, which is 14. 60 times 14 is 840 units cubed. Let's take a look at the volume of the smaller prism. Volume is equal to base area times height. My base area is the rectangle over here, which is 5 times 3, which gives me 15, times the height, which is 7. 15 times 7 is 105 units cubed. So if we compare the ratio of the side lengths, we'll see that the side lengths have a ratio of 2:1. And if we compare the ratios of the volumes, we'll see that the ratio can be written as 840/105, which can be simplified. And when you simplify it, you will get that the ratio of the volumes is 8:1. Notice that if you take 2 and raise it to the power of 3, you get 8. And if you take 1, raise it to the power of 3, you get 1. Which brings us to the theorem 12.13 of similar solids. If two similar solids have a scale factor of a to b, then the corresponding areas have a ratio of a squared to b squared, and the corresponding volumes have a ratio of a cubed to b cubed. Example number 2, using the scale factor of similar solids. Cylinders A and B are similar with a scale factor of 2 to 5. Find the surface area and volume of cylinder B given that the surface area of cylinder A is 96 pi square feet and the volume of cylinder A is 128 pi cubic feet. Begin by using theorem 12.13 to set up two proportions. We'll start by first looking at finding the surface area of cylinder B. We know that anytime we're looking for area, we're going to take the original ratio and square it, so it's going to be a square over b square. Since we know that the original ratio is 2 over 5, take 2 and square it, and 5 and square it. So 2 square is 4, 5 square is 25. We can set up a ratio of the surface area of A, which we know, over the surface area of B is equivalent to the ratio 4 over 25. Cross multiply to solve for B. We end up getting 96 pi times 25 over 4 is equal to the surface area of B. 96 pi times 25 is 2400 pi. Divide that by 4. And we get that the surface area of B is 600 pi. So the surface area of cylinder B is 600 pi square feet. Let's now take a look at the volume of cylinder B. We know that the ratio for volume takes the original length ratio and cubes it. So we would do A cubed over B cubed, which will lead us to 2 cubed over 5 cubed. 2 cubed is 8, 5 cubed is 125, and we can set up a ratio for the volume of cylinder A over the volume of cylinder B is equal to the scale factor cubed. Cross multiply to solve for volume of B, and we get 128 pi times 125. Divided that by 8. 128 times 125 is 1600. Divide by 8, and that's 1600 pi. 1600 divided by 8 gives me the volume of B, which is 2000 pi. So the volume of cylinder B is 2000 pi cubic feet. Example 3, finding the scale factor of similar solids. The two cones are similar. Find the scale factor. Since we know the two cones are similar, we can set up the ratio as A cubed over B cubed is equal to the volume of cone A over the volume of cone B. So we have A cubed over B cubed is equal to 108 pi over 256 pi. If you simplify this, pi divided by pi is 1, and 108 and 256 simplify to 27 over 64. To figure out what A and B are, you're going to take the cube root of 27 and the cube root of 64. Cube root of 27 is 3 and the cube root of 64 is 4. So the scale factor of the two cones is 3 to 4. Example 4, comparing similar solids. Two punch bowls are similar with a scale factor of 2 to 3. The amount of concentrate to be added is proportional to the volume. How much concentrate does the smaller bowl require if the larger bowl requires 48 ounces? Using the scale factor, the ratio of the volume of the small punch bowl to the large punch bowl is 2 to the power of 3 and 3 to the power of 3, which 2 to the power of 3 is 8 and 3 to the power of 3 is 27. If you take 27 and divide it by 8, you get that the ratio is approximately 1 over 3.4. I'm not a fan of this 1 over 3.4, so I'm just going to use 8 over 27 as my scale factor ratio. In order to find how much concentrate the smaller bowl will require, knowing that the larger bowl has 48 ounces, I'm going to set up a proportion of 8 over 27 is equal to the concentrate for the small bowl over the concentrate for the large bowl. I know that the concentrate for the large bowl is 48 and I'm looking for the concentrate for the small bowl. So cross multiply to isolate x, and we end up with x equals 48 times 8 over 27. 48 times 8 is 384. Divide that by 27 and we get that the smaller bowl is approximately 14.1 ounces. So the smaller bowl requires about 14.1 ounces of concentrate. Alright, checkpoint problems number 1 and 2 are yours. For both of these problems, decide whether the two solids are similar. All right, that's it from me. I'll see you all soon.